Every civilization in the universe is already dead, or it's dying right now, or it hasn't been born yet. Not because of war, not because of disease, not because some gamma ray burst happened to point in the wrong direction. Because of a law so fundamental, so ruthless, so completely indifferent to how clever you are or how many planets you've colonized, that no amount of intelligence, no amount of technology, no amount of cosmic ambition can touch it. Physics doesn't negotiate. It doesn't grant exceptions for civilizations that figured out faster than light travel or built Dyson spheres around their suns. The law applies to them too. It applies harder to them, actually. And here's what makes that genuinely interesting. We've known about this law for over 150 years. We derived it from steam engines. Steam engines. And buried inside that dirty, industrial 19th century physics is the precise mechanism by which time itself becomes a weapon pointed at every thinking thing that has ever existed or ever will. I'm going to show you exactly how that works. Not the vague, hand-wavy version. The real version, the one where you understand why it's inevitable, why there's no loophole, and why the universe being as old as it is makes the silence out there not mysterious at all. It makes it expected. You've never seen a broken egg fix itself. You've never watched smoke gather back into a cigarette. You've never seen a puddle leap off the pavement and reconstitute into a raindrop, heading back toward the cloud. These things don't happen. Not once. Not ever. You might say that's obvious. But here's what's strange. If you filmed any of those processes at the molecular level and ran the film backwards, you could not tell which direction was real. The individual collisions between molecules are perfectly reversible. Physics at the small scale doesn't care which direction time runs. And yet at the large scale, everything has a direction. Broken things stay broken. Mixed things stay mixed. Hot things cool down. There is a fundamental asymmetry baked into the universe at every scale we can observe, and for a long time nobody could explain where it came from. That asymmetry has a name. Entropy. And I want to be careful here because entropy gets thrown around in ways that make it sound vague and philosophical. Let me give you the real definition. Entropy is a measure of the number of ways a system can be arranged without looking any different from the outside. That's it. And it sounds simple until you apply it, at which point it becomes one of the most powerful and terrifying ideas in all of science. Imagine a box divided in half. On the left side, a gas, a billion molecules bouncing around. On the right side, nothing. A vacuum. You remove the wall, the gas expands and fills the whole box, every time. Without exception. Why? Because there are vastly more ways for the gas to be spread across the whole box than for it to be concentrated on one side. With a billion molecules, the number of arrangements where they all happen to be on the left is essentially zero compared to the total possibilities. So things drift naturally toward the states with the most possible arrangements. Not because a force pushes them, not because nature prefers disorder for some mystical reason, simply because there are more ways to be spread out than concentrated. Probability does all the work. Ludwig Boltzmann worked this out in the 1870s. He was trying to connect large-scale gas behavior, temperature, pressure, volume, to the small-scale motion of individual molecules. What he found, buried in probability mathematics, was that entropy always increases in a closed system because high-entropy states are so astronomically more numerous than low-entropy states that random motion will almost never take you from disorder back toward order. It's not impossible. It's just so improbable that waiting for it to happen naturally would take longer than the current age of the universe multiplied by a number that doesn't fit on this page. The arrow of time is just probability applied at such extreme scales it becomes effectively absolute. But Boltzmann's insight raises a deeper question. Why was entropy ever low to begin with? The gas only expands because it started on one side. The egg only breaks because it started whole. For time to have a direction at all, the universe had to start in a state of very low entropy. And it did. The Big Bang was not a chaotic explosion in the way people picture it. It was, thermodynamically, an extraordinarily ordered event. Matter and energy in the early universe were distributed almost perfectly uniformly, with fluctuations of only 1 part in 100,000. That is an unimaginably low entropy starting condition. And everything since, every star, every planet, every living thing, every thought, is the story of that initial order, slowly, irreversibly degrading. You are a low-entropy structure. Your body takes in food, organized molecules, stored sunlight, converts it into heat and motion and thought, and expels carbon dioxide and waste heat. The food you ate was more ordered than the waste you produce. Every metabolic process you run takes something structured and makes it less structured. You are, in the most literal physical sense, a machine that converts order into disorder in order to maintain your own local order temporarily. And when you die, that local order dissipates. The entropy you were holding at bay catches up. This is not poetry, it's thermodynamics. Scale that up. A civilization is a vastly more complex version of the same thing. It takes low-entropy resources, coal, oil, sunlight, nuclear fuel, converts them into useful work and produces waste heat and used-up material. The civilization persists as a local pocket of order only as long as it has access to low-entropy energy. When those sources run out, it has a problem. Not a political problem, not an economic problem, a physics problem. And physics problems don't get solved by elections or revolutions or optimism. They get solved by physics, or they don't get solved at all. Here's what people miss about energy. It's not just about having energy. It's about having usable energy. Water behind a dam has usable energy. It can fall and turn a turbine. Water at sea level has the same total energy in some technical sense, but it can't do useful work without somewhere lower to fall. The universe is full of energy. The total amount never changes. That's the first law of thermodynamics. But the total amount of usable energy decreases constantly. That's the second law. The universe is running down not by losing energy, but by converting usable energy into unusable energy, order into disorder, structure into noise, and this process has no reverse gear. Rudolf Clausius stated this precisely in 1865, 2 sentences that should be on the wall of every university in the world. The energy of the universe is constant. The entropy of the universe tends toward a maximum. 2 sentences from watching steam engines, and they describe the ultimate fate of every complex system in the cosmos. The first sentence says, you can't win. The second says, you can't even break even. Now let's talk about what this means for life specifically. Life appears to violate entropy. A cell is an extraordinarily organized structure. Thousands of different molecules in precise configurations, carrying out specific functions, replicating themselves with stunning accuracy. That's low entropy. That's order. So how does life exist at all? The answer is that the second law applies to closed systems. Life is not a closed system. Life exports entropy. It takes in low entropy energy, does useful work, and dumps high entropy waste back into the environment. The net entropy of the universe still increases. Life just arranges the accounting so that its local region stays ordered while the environment pays the bill. This is the crucial point. A civilization can maintain itself, even grow, even increase its complexity, but only by increasing the entropy of its environment even faster. There is no free lunch. Every bit of order you create is paid for with more disorder somewhere else. The more complex a civilization becomes, the more energy it consumes, the more entropy it generates, the faster it burns through available low-entropy resources. Complexity is expensive, intelligence is expensive, and the universe issued a finite budget at the beginning that has been shrinking ever since. Here are some numbers to keep this concrete. The sun outputs about 3.8 times 10 to the 26th watts of power every second. All of human civilization currently uses about 2 times 10 to the 13th watts. The sun outproduces us by a factor of roughly 20 trillion. We are not even a rounding error in its energy budget. A Type 2 civilization on the Kardashev scale, one that captures all of its star's energy output, would be using that full solar output. That sounds like unimaginable abundance, but the sun is a nuclear furnace running on a finite hydrogen supply. It has burned for 4.6 billion years and has roughly 5 billion years left. 5 billion years sounds like forever. In thermodynamic terms, it's a deadline. Enrico Fermi sat down for lunch at Los Alamos in 1950 and asked a question nobody had framed so directly. Where is everybody? The universe is 13.8 billion years old. It contains between 200 billion and 2 trillion galaxies. Each galaxy holds hundreds of billions of stars. Many have planets. Some are at the right temperature for liquid water. Some have chemistry. Some have biology. Some have intelligence. The numbers are so large that even with conservative estimates, you end up with enormous numbers of potential civilizations. So why is the universe silent? Why in over 60 years of radio telescope observation have we heard nothing unexplainable by natural processes? Many answers have been proposed. Great filters, barriers that civilizations fail to cross. Maybe life is rare. Maybe intelligence always destroys itself. Maybe interstellar travel is impossible. These are reasonable proposals. But there's one filter that doesn't get enough attention because it requires taking thermodynamics seriously at cosmic scales. The filter might not be any single catastrophic event. It might be the slow, inexorable degradation of usable energy. Every civilization, no matter how advanced, eventually hits the same wall, not a wall of technology or politics, but a wall of physics, the wall where free energy runs out. Think about what a civilization needs to persist indefinitely. A continuous supply of low-entropy energy, and the universe is systematically, irreversibly converting low-entropy energy into high-entropy energy. The stars are burning out. In about 100 trillion years, the last red dwarf stars will exhaust their fuel and go dark. After that, there are no more natural sources of low-entropy energy. There are black holes radiating very slowly via Hawking radiation, but over timescales that make the current age of the universe look like a fraction of a second. There are white dwarfs cooling over trillions of years. But all of this is just the universe completing its drift toward maximum entropy, toward heat death. A condition of perfect, uniform, useless thermal equilibrium where nothing happens because there is no gradient left to drive any process. This is where intelligence and thermodynamics really converge. A brain is a physical system that processes information. Information processing requires energy. Rolf Landauer at IBM worked out in 1961 that erasing a single bit of information requires a minimum amount of energy and produces a minimum amount of entropy. This has been experimentally verified. It means that thinking, actual computation, actual cognition is tied to thermodynamics at a fundamental level. There is a minimum energy cost to every thought, every memory, every decision. You cannot think without producing entropy. Intelligence itself is subject to the second law. This means the total amount of thinking any civilization can ever do is bounded by its energy supply. A civilization running low on energy must choose which computations to run, which structures to maintain, which processes to prioritize. Energy scarcity is cognitive scarcity. It's not just lights going out. It's thoughts becoming impossible. And the most advanced civilizations, the ones that have built the most complex internal structures, need the most energy just to hold themselves together, not to grow, just to maintain their current state. The energy cost of complexity scales faster than linearly. Doubling the complexity of a system more than doubles its energy requirements. So the most sophisticated civilizations are also the most thermodynamically fragile. Freeman Dyson argued in 1979 that a sufficiently clever civilization might find ways to keep thinking indefinitely by slowing its computation rate as the universe cools, doing more with less energy over time. It was a genuinely creative proposal, but Lawrence Krauss and Glenn Starkman showed in 2000 that in a universe with a positive cosmological constant, which ours appears to have, even Dyson's optimistic scenarios break down. The accelerating expansion of the universe means the accessible pool of low-entropy energy shrinks faster than stellar burnout alone would suggest. Galaxies are receding from each other at accelerating rates. In a few 100 billion years, the Milky Way and its nearest gravitational companions will be the only matter we can reach. Everything else will have crossed the cosmological horizon, forever inaccessible. The universe is not just running down. It's pulling apart, isolating pockets of matter, reducing the resource base for anything trapped within them. The Kardashev scale is usually presented as a ladder of progress. Type I uses the energy of a planet. Type 2 uses a star. Type 3 uses a galaxy. Each rung is supposed to be better than the last. But thermodynamically, it's also a ladder of exposure. Each rung means you've built complexity that requires a vast energy supply to persist. When that supply starts contracting, and it will, because the stars burn out and the universe expands, the fall from higher rungs is longer and harder. A Type 1 civilization facing energy scarcity gives up conveniences. A Type 3 civilization facing energy scarcity watches the infrastructure of its entire existence dissolve. The universe started with a finite endowment of ordered, usable energy. That endowment is the only reason anything interesting has ever happened. Every star, every planet, every cell, every brain, every civilization, every thought ever produced drew on that initial account. It was a one-time gift. It cannot be replenished. And we are all, every living thing on every planet, around every star, spending it. We exist in the interval between the ordered beginning and the disordered end. We are the entropy happening. And somehow, in the middle of that process, matter arranged itself into configurations that could look around and ask why, that could build telescopes and thermometers and steam engines and eventually derive, from watching pistons and pressure gauges, the mechanism of its own impermanence. Clausius's two laws came from engineers trying to build better machines. They were not trying to describe the fate of civilizations. They were not trying to explain the silence of the sky. They were trying to get more work out of steam. And what they found, buried in the math of heat and efficiency, was the deepest fact about time, that it flows in one direction, that it flows because of entropy, and that it will flow until entropy is maximized, and then there will be nothing left to drive any process anywhere. When you look at the night sky, you are looking at a thermodynamic machine in the middle of its slow, irreversible wind down. Every star is a furnace converting hydrogen into helium, releasing energy locked in the universe's initial low-entropy state, radiating it out as waste heat into the cold dark. Beautiful, blazing, temporary. Some of those stars are already gone. The light you're seeing left them before you were born, before your civilization existed, and the source has since burned out. What you see is a record of the past, written in light, describing processes that are steadily consuming what the universe started with. The silence out there is not a mystery. It's a prediction. The second law predicted it. Before we ever built a radio telescope, every civilization that rises draws on the same thermodynamic budget, faces the same direction of time, hits the same ultimate wall. The ones that came before us, if they existed, are gone, not because they failed, but because the universe they inhabited was always running the clock, and we are not special in this regard. We are not exempt. We are not early enough to avoid it, or clever enough to escape it. We are just the latest configuration of matter to figure out the rules of the game, late enough in the universe's history to see the ending coming, and early enough that the ending is still very far away. That window, that thermodynamically precious, cosmologically brief window between the ordered beginning and the disordered end, is what we have. The universe produced, out of its own unfolding, the means to understand its own unfolding. That is not nothing, but it doesn't change the physics. The second law applies to the remarkable and the unremarkable alike. It applied to every civilization that ever rose far enough to wonder about the silence of the stars. It applies to us now, doing exactly that. Every civilization in the universe is already dead, or it's dying right now, or it hasn't been born yet. And the reason isn't weakness. It isn't failure. It isn't bad luck. It's written in the physics of heat and time and entropy, the same physics that a French engineer and a German mathematician worked out from steam and pistons 150 years ago, long before anyone dreamed it would one day explain why the universe, for all its size and age, sounds so completely, perfectly, inevitably quiet.